Okay. Hi everyone. Um Welcome to the fourth problem solving session. Okay. And again, my name is Bhavya. Okay. And we are holding these classes from Tuesdays, every Tuesdays, 6 p.m. to 8 p.m. So last week, what did we see? Last week we saw the power of randomization, and then we saw polynomial identity testing (PIT), and we saw concentration inequalities. And we did what a Bernoulli variable is, a random variable. Okay, okay. We did these things. Okay, some things I could not cover was perfect matching. But I hope you guys saw the lectures. But in case you want me to discuss about it, then please let me know. Okay. So these were the things we did, and I looked at the assignments whose deadlines are over recently, the week three assignment, and week three was more or less based on these topics, and more or less the questions were not did not look too challenging. That's what I thought personally. So, but let me know if you want to discuss it still. Okay. Having said that, so this time the content is not much, so this will be a much shorter session today. Okay, and so this will be a much shorter session. Um, it won't. So there are very proof based and theoretical concepts in this time, but as far as applied applications go, I mean, it's not applicable really, but the lectures are need a few more concepts to be covered before we can fully dive into applications. Okay, but still, I've collected a few questions that I want to discuss. Okay, and this will probably be a very short session. Okay, but we it's if you want to discuss more, then we can discuss till 8 p.m. That's not a problem. Okay, so having said that, let's begin. So what are the concepts that are there this time? So you have the concept of um, firstly the coupon collectors problem. You have the concept of okay uh, coupons collectors problem. You have the concept of balls and bins, and well, you have 2 point sampling, but again, writing questions for this is requires some more concepts to be covered. So mostly I will be doing coupon characters problem and balls and bins, and we'll be discussing probabilities and such. Okay, and finally we have randomized algorithm for 2SAT. Now this is again a very specific topic. So so let me begin by okay. Just doing a very slight recap. Okay, and that is um we have the concept of random bits. Okay, randomness shows unpredictability, and why is randomness good? Well, um, more efficient algorithms. Not always, but in most cases, you could get more efficient algorithms. Okay, and why? And because it avoids corner cases. And why is randomness bad? Well, we don't know. a good source of randomness. Okay, and this source of randomness thing I want to discuss in detail in next week. Okay, which is about 2-point sampling. But right now I don't want to get into it. Okay. Um, Now, what do I mean by a good source of randomness? Well, how do you actually obtain random bits? How do you make sure that whatever you do is truly unpredictable? Let's say you are writing an algorithm. What would be a good source of random bits for it? Well, you can't make um, the computer toss coins, right? Or even if you make it toss the coin, is it completely random? Well, that is arguable, and if you could use something like maybe noise from the environment or the fluctuations, minor fluctuations in temperature and so on, but we don't know whether each of these processors are purely random. Okay, and I don't know, good source of randomness. The other bad thing about randomized algorithm is that we don't know, there could be error possibility. Okay, and so on. And we saw that there could be two types of errors. Okay, there could be two types of errors, and one-sided and two-sided. And uh, another way of categorizing was in terms of Las Vegas algorithms and Monte Carlo. Now, this Las Vegas is always correct, and sometimes slow. What do I mean by sometimes slow? Well, across all instances of inputs, it does not take polynomial. It may not take polynomial time. In some of them, it may take exponential time. Okay, sometimes that is exponential time. And but what is why do we care about algorithms if it takes such a long time? Well, on average, on expectation, the expected running time is polynomial. Okay, and Monte Carlo is fast, that is polytime, but errors. So these two types of algorithms, that one-sided error, two-sided error, is all about Monte Carlo. It's all Monte Carlo algorithm. Okay, and so these things are done. But now, a few terms. What is expectation? Expectation of x is defined to be so if x takes value, a1, a2, and so on till ak, then it is a1 times probability that x equals a1 plus a2 times probability that x equals a2 and so on till ak times probability that x equals ak. Okay, and so actually it's, yeah, this is fine, right? So and what is Markov's inequality? It helps us in analyzing success probability of algorithms, and it says probability that a random variable is at least a is at most the expectation of x, which is the expectation of x divided by a, right? And we saw some applications. One of the applications we saw was on analyzing, the worst case versus average case of algorithms. If the average case is, if the worst case is, the higher the worst case, the worse the worst case, the more improbable it is that we will actually reach the worst case, because the average case actually balances it out. So that was one nice example that we saw last time. Okay. Okay. Now all that thing is done. So Let's talk about solving some problems, okay? And then I'll go back into theory and then let's continue, okay? So those are some preliminaries. So here's the question, okay? Yeah, here is an interesting question. So I think you have noted that um, the algorithms that I create, randomized algorithms, suppose I have a problem, okay? Suppose I have a problem P and I want to make a randomized algorithm for it. I was always interested in, if you look at definitions of, say, uh, one-sided error algorithms, so say something like it says yes correctly with probability greater than half and no with probability less than equal to half, right? And it goes something like this. Now, why is it? Why is half chosen? What's so special about half? That's one question we would like to know. If is it like what if I say the following that my algorithm makes an error with a probability of 1/4 on both sides. It says yes with an error of probability. Sorry, it succeeds with an error of succeeds with a probability 1/4 and makes an error of 3/4. Okay, that is succeeds with probability 1/4. Now, I want to say that what I claim is that such kind of algorithms are useless to me because the success probability is less than half. Now, why is it so? Any idea? Or rather, look at the statement of the question. Show that for any decision problem P, it is possible to obtain a randomized algorithm with error probability at least 0.5. So, this is a fundamental question that I want to address before moving on to anything. Okay. So, what I'm saying is, given a problem, I can always make a randomized algorithm where error is half. Error is not even at least, sorry, error is at most half. Yeah. Sorry, who was it? I was looking down. Yeah.
So, so I flip a coin. If it is head, then the answer of the decision problem is yes, and if it is coin, then the answer of the decision problem is no.
Exactly. Exactly. So, one moment. Okay. Huh. So, claim is for any decision problem. Now, what is a decision problem, by the way? It is a problem where the answer is yes or no. Okay. Any decision problem. We can always construct a randomized algorithm for the problem okay for any decision problem we can always construct a randomized algorithm for the problem with error probability at most half. Okay, with error at most half. Now it's interesting, right? But actually this answer is quite simple. So given a problem, P, okay, I simply toss a coin. If heads, then output yes. If okay, toss a coin. If tails, then output no. Okay, toss a coin. If heads, then yes. If tails, then no. And that's it. So this seems very it seems like cheating, but well, what is the probability? Okay, let's say um, the problem is graph isomorphism. Is one graph G1 isomorphic to another graph G2 or not? Let's say G1 is isomorphic to G2. And let's say I toss the coin and it comes to heads. Great, well, I said yes anyway. And if I toss the coin, then it comes to tail. But what is the probability that I make an error? Well, the probability that the probability that I make an error is that I toss the tails, right, which has a probability of half. So it says yes with a probability of half anyhow, and it says no. Okay, so if answer is yes, then then if error toss says okay, toss says yes, toss says tails, probability that toss says tails is equal to half. So this is nothing but the error probability. Because note that toss says tails is same as saying algorithm says no. And if the actual answer is no, then probability that toss says heads is equal to half. This is equivalent to saying the algorithm says yes. Because if there was a heads, then I'm saying yes. So now I hope you can see that why is it important that I have error probability of half. Why this is the case, right? So sorry, error probability of at least more than half. Okay, I cannot guaranteeing the half. Yeah.
Yeah. See, of course, for a decision problem, fine. We make we think probability of error is at most half.
Right.
Yeah, but what about the other problems, like other than decision making problem? Because as per the question, right, it hasn't said any decision making problem. It just said given a problem.
Oh yeah, no. Question said decision problem, right? Oh wait, where am I? It says a decision problem.
Oh, is it? Okay. So this is, of course, then that what we are discussing is in a right way, but just in case the problem is other than decision problem, do we also consider the same algos or some other way we have to do?
Yeah, you cannot say the same for a search problem, because see, if you have a search problem, okay, if it's now something like find the isomorphism, okay, search problem. Okay, search problem says find this isomorphism G1, G2. Let's say that is sigma. What is an isomorphism? It means that I can relabel the vertices and still the graph will look the same, right? Or formally it is there is a permutation sigma, okay, there is a bijection sigma from the vertex set to the vertex set, okay, such that if uv is an edge, if and only if sigma u sigma v, the vertices that it gets mapped to also has an edge here, and this is true for all uv. Okay, this is what a permutation is. This is what a isomorphism is, right? Now I want to say that find the isomorphism if exists. Okay, find the RF isomorphism if it exists, right? So question is, how many possibilities are there? Before it was just yes and no, right? The answers were just yes and no before. Right now, what are the possible answers? How many answers? How many possible answers are there? That is the question, right? How many possible answers are there? Well, that should be equal to the total number of permutations possible, right? The total number of isomorphism possible, right? The same as total number of isomorphisms possible. Right. I mean the number of outputs possible. Right. So let's count the number of outputs. It's a simple counting argument. You've heard it before. I think the number of bisections. So here's the vertex at B. Here V here's the same vertex at B. This is vertex 1. This is vertex 2, 3, and so on till vertex n, and again 1, 2, 3, and so on till vertex n. Okay. And now you ask how many are there? How many choices are there? Well, the first permutation could choose any of the n
number of ways.
Yeah. And now the second vertex could map to any of the, let's say, now let's say we fix one. Let's say the first vertex is mapped to first vertex.
Yeah, I think it's n to the power of n vertices.
N to the power n.
Right. N to the power of n.
No, but that is not true. That is not right, because that would be if this is a permutation. Remember, this is a bijection. It is not an injection. Okay, I cannot have multiple in a particular permutation. I cannot have 1 mapping to 1 and 2 mapping to 1. I need 2 to map to another vertex. You get it, right? It should be a unique mapping.
Okay.
Something like this should not be allowed. This would mean that I am in the graph context. What does it mean?
But it's 1 to 3 is already mapped, and then we are still mapping from 2 to 3, right?
Yeah, no, exactly. That's why it's not n to the n. Right, correct. So let's say 2 gets mapped to 3. Okay, how many choices did 2 have? 2 did not have 1 as a choice. That is the reason why it's not n to the n. 2 does not have 1 as a choice because 1 is already gone. Because 1 is already mapped. 1 is already mapped to itself.
So it should be just like a perfect matching. We should have that. We should consider here.
Yeah. Another way to think of it is how many perfect matchings can there be.
Okay.
Okay. Another way to think about it. So 2 is mapped. 2 has actually choices from 2, 3, and 4, and so on. But let's say 2 gets mapped to 3. And you get the idea. And you get the idea, right? So
right.
The first vertex has n many choices. The second vertex has n minus 1 many choices. Third vertex has n minus 2 many choices, and so on and so forth until the last vertex has just one. Exactly, there are n factorial. So how many isomorphisms are possible? N factorial many. Okay. So now if I give you, okay, good. So now if I give the same argument that you have a search problem, you are given 2 graphs and you are supposed to give a half error algorithm, okay, probability at most half error algorithm, and your strategy is to toss coins and give a random permutation. Before you were doing that, right? Your answer solution space was yes or no. You are tossing a coin and choosing either yes or no. Now, how big is the solution space? N factorial. Right? And how many coins do you have to toss? Well, N factorial many coins. To choose among the... Maybe you can be a little bit more clever using some binary encoding. Okay? But you will still require at least polynomial many. Actually, you will require exponentially many. coin tosses to actually do this, right? So and even if you do it with polynomial, okay, you could do something like, so there are n factorial, and n factorial is really large. It's like what, n to the n. It's bounded, upper bounded by n to the n, which is something like 2 to the n log n. And even if you say, if this is the first isomorphism sigma 1, this is the second isomorphism sigma 2, sigma 3, and so on, sigma 2 to the n log n, and let's say you become very clever, you choose to encode these indices in binary, okay, so that you need to toss fewer coins, okay. And since there are how many, 2 to the n log n many, I can index each of these, okay. This is the m, okay. I told last time that, if there are n bits, then it can encode how many numbers, 2 to the n numbers. So we are doing the opposite here. Here we have 2 to the n log n, so it can be, each of these can be indexed by a bit string of log of 2 to the n log n, which is equal to n log n. So I toss coins here, okay, and this becomes tail, head, tail, and whatever, okay, and I'm able to index, and I say, okay, sigma 1 and so on. I get rid of the possibility of I need too many coin tosses. Okay, fine, I am done with polynomial. But what is the problem again? Well, the problem is the success probability. Success probability. Okay, what is the chance you make an error? What is the probability that this is a correct permutation? It is 1 by 2 to the n log n. So success probability is so small. It's 1 by 2 to the. It could be any of the permutations, right? So its success probability is very low. So even if we become clever and we don't toss so many coins, the success probability is still very low. So we cannot get half like as before, right? Kishore, is that right?
Right. And probably I think I just randomly got an idea. So sometimes if the what you say is the calculation is so complicated, I think we can even implement these arithmetic and then geometric progressions, and then we can get the solutions, right?
So calculations are so complicated. What calculations?
I mean, this is the same thing. See, now we have to toss the coin n factorial base, right? So if the pattern is similar to the arithmetic progression, or if the pattern of tossing the coin is in terms of geometric progression, then I think implementing the mathematical equation will get to a solution, right? Is it possible?
The pattern of tossing coins is a geometric progression. So what do you mean by? Okay. So you mean the 0 1s are spaced out in a geometric progression or something like that?
Right. Because see here, how do we concluded is n factorial is based on the pattern of the toss. Any n first time and the second n minus 1 and second third n minus 2. So that's where we have concluded as n factorial base.
Oh, okay. But I think what you mean. Oh, okay. Yeah, the pattern. That's correct. Yeah. The pattern decides which permutation I choose at the end, right? If it is, say for example, if it is all zeros, then I'll choose this one. If it's all zeros followed by 1 and 0 0 1 0, and I keep doing this in binary, 0 0 0 1 1 and so on. I keep doing this in binary. It's the pattern that dictates. Correct.
Okay.
Yeah. So but now, like you said, if the pattern is something in like arithmetic progression or geometric progression, problem is now that your coin tosses are no more random.
Oh, so
there is some probabilities now, right? I mean, since there is as soon as you talk about patterns, it becomes less random. Because what does it mean to be random? It means that there is no pattern.
Okay. Yeah.
Right. So that is there. So yeah, the success probability becomes incredibly low with this approach for search problems. Okay. Yeah, but thanks for bringing that up. Okay, great. So, okay.
And the small thing that this graph isomorphism is not NP complete. This is somewhere NP intermediate.
Yeah, yeah, that'll complete it. Right, right. Yeah, this is not an NP complete problem, but it's a very difficult problem, which does not this. Yeah, by the way, this graph isomorphism problem, we don't have a polynomial time solution. Okay. Do we have a randomized algorithm for graph isomorphism? I am not sure about that.
Yeah,
Whether
but then there is an algorithm which runs in an effort of the order of n raised to the power of the order of log n.
Yeah, there is a n raised to the power log n. This is a Babai result, which was I think in 2020.
2015.
2015. Okay, 2015. Yeah, Babai. Yeah, this is he gave an n to the log n, which is a pseudo polynomial algorithm, and it's still not polynomial, but it's a huge breakthrough. And yeah, the paper is some 150 pages long. So yeah, it's a very non-trivial algorithm that he has. Yeah, so okay, so let's talk about the second one. Okay, so here's the question: suppose Bob decides to play a game in a casino. In each round, Bob tosses a fair coin. If the outcome is heads, Bob gets 50 rupees, and if it is tails, Bob loses 50 rupees. Okay. Now, if Bob plays 10 games, how much is Bob left with on expectation? Okay, let me take a screenshot and paste it. Okay. So, okay, so here's the question. So question is, suppose Bob decides to play a game in a casino. Okay. So what is the game rules? Toss a coin. Okay. Toss a coin. If coin is heads, okay, then you win or Bob wins 50 rupees. Okay. And if coin is tails, then you lose 50 rupees. Okay. Now, let's say Bob can play on credit. Okay, even if he does not have any money, he can accumulate negative debt. Okay, so if Bob plays 10 games, how much is Bob left with on expectation? So what do you expect Bob to win at the end? So even if you don't have the calculations, you can think of it intuitively also. Intuitively, what do you feel? How much will Bob win?
So expectation of a single game would be that Bob would be earning 50 rupees with a probability of half, and Bob would be losing with 50 rupees with a probability of half again.
Yeah.
So in one game, the expectation would be equals to 0, as if he's not gaining anything.
Right.
And now the Bob is playing 10 games. So assume that every game is independent of one another. So now a linearity of the expectations. So I would be adding this expectation say 10 times.
Okay.
So then the value came out to be 0 again. What do you think?
Okay. Yeah. Good. Is that? Did you guys agree with him? Or maybe I'll explain it once. Okay. So yeah, let's do it the expectation way. So we want to say Bob plays 10 games. How much is Bob left with on expectation? Okay. Now, let's say X is the total amount of money Bob is left with after 10 games. Okay. Now what we want to do is, we want to define, let's say, an xi. Okay, xi is what? A Bernoulli variable. Okay, what is a Bernoulli variable? It is a variable which can take any value, but the probability of it occurring is exactly half. Why am I using this? Because I can actually, I think someone had asked last time, right? What if instead of 0, 1, oh, okay. Sorry for that. I'll just plug in. I think it's another, but I'll just finish explaining this before I need to charge. Okay, so xi, I'll define it to be 50 if or yeah, let's define it more simply. Let's do it more simply. Okay, simple case, simpler case. That is, Bob plays one game. Bob plays one game. Okay. Now, what is the expectation of the amount of money that Bob gets? Okay. So the expectation. So let's say X is the amount of money Bob wins or loses. But Bob is playing just one game, remember. So in one game, he can either win 50 or lose 50. So since he's either winning 50 or losing 50, I can define X to be 50 if Bob gets heads. Okay. So what is the probability? Probability is half, which P of X is half, and P equals half. And he loses 50 if P equals, and 1 minus P, with probability 1 minus P, which is half. Okay. So on expectation E of X, okay, what is it? It is 50 times probability that X equals 50 plus minus 50 times probability that X equals half. X equals 50 minus X equals not X equals 50. Okay. So what is this? 50, X equals 50 with probability of half plus minus 50 half, which is equal to 0. So in one game, the probability that the expectation of the amount of money that Bob wins or loses is 0. Okay. So now what we have is he's playing 10 games. Now we assume that each of the 10 games are independent from each other. Okay, because it's only natural that one game does not affect the other because it's simply a coin toss, right? So now we define X to be the total amount of money Bob is left with after 10 games. Now, XI, each game, same thing. Bob 50, if heads, that is probability is half, and minus 50 with probability 1 minus P, right, which is half. And now what do you have? We want to find expectation of X, which is expected total amount of money Bob is left with after 10 games. Now observe this following fact, that expectation of X is nothing but expectation of 1 plus x2 plus x3 plus so on till x10. Why? Because it's not a property of expectation, okay, that I'm using. It's just simply that I'm replacing X, which is the total amount of money Bob is left with. Bob wins or loses, and I'm summing up each of these. So let's say x1 is 50, x2 is in the next one he lost minus 50, next one he won 50, and so on. So you can easily substitute x for x1 plus x2 plus x3, right? So you can also say, just say it separately, that x equals x1 plus x2 plus and so on, x10. Now what do you do? Now by linearity of expectation, which we saw last time, I can split it into several parts like this by linearity of expectation. Okay, and what do you have? Each of these x1s are independent. So each of these x1 to x2s are independent. And what do we know? We know that each of them, each of the coin toss leaves a value of expectation to be 0. So expectation of x1 is 0 plus expectation of x2 is 0 plus and so on till 0. Okay, so the answer is 0. So if such a game is played where it's purely random, then, and it's kind of intuitive also, right? That we'll see heads and tails more or less at the same number, same frequency. So therefore, Bob should not be winning or losing anything. Okay, it'll all get cancelled out. So yeah, I'm going to get my charger. Please try part B. Okay, what is it? Okay, it's 4%. Okay, please try part B. Okay.